So here in this arrangement is given in the question for the planar mechanism shown in the figure. Select the appropriate motion choice. Select appropriate choice for the motion of link number 2 when link number 4 is going to move upwards. So if the link number 4, this is link number 1, once again it is fixed. So if 4 is moving upwards, then this is going to push the link number 3, or link number 3 is going to experience rotation like this. Okay, it is going to experience the rotation like this, and then that is going to further cause the rotation of link number 2 in the counterclockwise. So here just that you have to investigate what is the direction of motion of link number 2 only. So option A says that counterclockwise. So option B says that link 2 rotates in counterclockwise. Yes, that is the exact answer we are getting. And link 2 does not move, so that is not an appropriate answer. Link 2 motion cannot be determined. So if that is not determined, then it's difficult to predict the mobility of the mechanism. Okay, so this is a very simple process we try to apply when we are checking the mobility of the mechanism. So one type of question was framed from such approach. Okay, so option B is the answer. Next question. In an instantaneous center for a body rolling with sliding on a stationary curved road lies dash. So instantaneous center for a body which is rolling and sliding, it's rolling plus slipping, both the things are happening on the on the stationary curved surface. So there is a stationary curved surface, and on this stationary curved surface a body is undergoing pure rolling motion? No, it's rolling plus slipping motion. So where is the eye center that is going to lie? So this is surface is fixed. So let's call it as 1 and let's call it as 2. So between these two, we find that a higher pair is always formed. Rolling motion occurs in the higher pair. So whenever there is a higher pair formed, the eye center for such case lies on the common normal. This would be common normal. This is going to be common normal. Okay, let's check. At the point of contact, yes, if it is a case of rolling motion, but it is not the rolling motion. Next, on the common normal at the point of contact. Even here also it says at the common normal at the point of contact. Okay, let's check the option C. It says at the common tangent at the point of contact. Definitely this has to be discarded, and point of contact, even option A, needs to be discarded because it is going to be there when the motion is pure rolling. When the motion is pure rolling. Okay, and next, at the center of curvature of the stationary surface. Is it? Here, if we try to understand at the center of the curvature, which means the body is tending to move about the center. It is moving around the circumference and about the center it is going to move. So, which means this body will not have any rotation about its own axis. Okay. So, here it is mentioned about more about rolling and sliding motion, both has been included. If it is pure rolling motion, then at the point of contact, the eye center is expected to lie. So as per the question, option D cannot be the answer because reason is that the body will be in curvilinear motion based on option D. Not possible. And option C, it says that common tangent, no, it is always on the common normal. So we are left with only common normal and at the point of contact. So reason is that the sliding motion could be also discarded. More or less we are focused on rolling motion. Even option B is more appropriate answer based on the rest three. Okay. So option B is the answer. Try to understand that. If they include rolling plus slipping motion, then it has to be somewhere on the common normal. But if slipping motion is there definitely, then it will not be at the point of contact. it will be either above the point of contact or it would be either below the point of contact. Depends how, if we compare this rolling motion, if the rotation is greater than sliding motion or is the sliding motion more than the rotation. Based on that, the location of eye center can be predicted once we are able to draw the velocity gradients. Okay, so as per the question, we can only limit ourselves only to the option B, because A, C and D are not the right choices. Okay. Here in next question, we are required to predict the mobility as and when we see this arrangement directly and the link numbers are given to us. Just straight away try to read the keyword, one of the keywords, number of degrees of freedom, so which is more or less talking about mobility of the mechanism. So that's how you'll be able to save the time, and then rather than reading the question, just see the diagram itself and try to extract the information from there itself. So here it is, link number 1, 2, 3 and 4. So 5 links are given to us and you can find the 5 distinct joints, J1, J2, J3, J4 and J5. So 5 distinct joints are there. So J is equal to 5 and no higher pairs as such. So according to Grubler's equation, degree of freedom is equal to 3n minus 1 minus 2j. Okay, so 3 into n is 5 minus 1 minus 2 into 5, which is equal to 12 minus 10, which is equal to 2 degrees of freedom. So this is an unconstrained mechanism. So as per the question, option C is the answer. Next question we have, a figure shows quick return mechanism. The crank OA rotates in clockwise sense uniformly. OA is equal to 2 centimeters. OO dash is equal to 4 centimeters. The ratio of time for the forward stroke to that of return stroke. So since it is a quick return mechanism, the return stroke time duration has to be definitely less. So herein, if I write it as QRR, that is cutting time divided by time for the return stroke, this has to be greater than 1. So this is, if this is greater than 1, or this can be replaced with theta cutting divided by theta return also. Okay, theta return also. And here if we observe the sizes of fixed link and the crank, the fixed link size is more than the crank, and this is a crank slotted lever mechanism, not a Whitworth mechanism. So here if you check the ratio of these lengths, if it comes out as 2, directly QRR could be 2 only. This is a special case where you compare the lengths of fixed link and the crank. If that ratio is 2, then the answer could be either 2 or 0.5. Let's check here. They are asking us to express forward angle to the forward time to the return time. So it's the forward, in the forward motion the cutting happens, obviously the time consumption will be more, and in the return no cutting happens. It's an ideal stroke, so time should be very less compared to forward. So that's how from this definition we can judge that the answer is 2 directly. So if they had given this is in reciprocal way, like QRR is expressed as T return time by cutting time, then answer would be 0.5. So as per the question and the statement and data, whatever is available to us, based on that, option B is the answer. Next question, a rod of length 1 meter is sliding in the corner as shown in the figure. At an instant when the rod makes an angle of 60 degrees with the horizontal, the velocity of point A on the rod is 1 meter per second. So A is descending down with 1 meter per second. The angular velocity of the rod at this instant is dash. So this is velocity of A, and velocity of point B should be towards right side. So this is VB. As we know the velocity vectors, we need to draw perpendiculars from those velocity vectors. So I am marking, or I am drawing a perpendicular from VA and I am drawing perpendicular from VB. So wherever these two perpendiculars intersect, that would be an eye center. This becomes the eye center. Alright. So here we know the length of the hypotenuse, and IA will be equal to, that is 1 times of cos 60 and IB will be equal to, that is 1 times of sine 60. Now that we can apply the angular velocity theorem, that is velocity ratio theorem, that is VA by IA is equal to VB by IB is equal to omega. So VA is known to us, that is 1 meter per second, and IA is 1 into cos 60, which is 1 by 2. This is equal to omega. So here we get omega as 2 radians per second. So option A is the answer. Let's see the next question. So here it says audio cassette mechanism shown in figure given below, where the eye center of rotation of two spools. So we are required to locate where is the eye center of rotation for the two spools. So here if we start the numbering, this would be link number 1. Let's call this bigger spool as link number 2, and the tape or the belt as link number 3, and the smaller spool as link number 4. Okay. So as per the question, if we try to understand, they are asking us to locate the instantaneous center for the both spools, which means it's the I24 that needs to be located. Okay. All right, fine. Let's go through the options here. What does it say? Point P lies on the left of both spools at an infinity distance along OH, A and H. So it is going to lie on the left of both the spools. Okay. Let's try to examine here the sense of rotation. So if the right spool is trying to wind the wire, okay, if this is rotating in counterclockwise, then this has to get unwounded. The link number 2 should be unwounding the thread or unwounding the tape, and then the link number 4 will be wrapping the tape around itself. That's how the mechanism works, which means the sense of rotation of 2 and 4 should be same. Okay, so if the sense of rotation of 2 and 4 is same, this I24 is called as relative eye center. Relative eye center. So this relative eye center has to be on one side of these spools. If it is in the middle of two spools, then the sense of rotation will be opposite. That's the point you need to remember. So going back to the option B, that point P lies between two spools on the line joining A and H. Between two spools. This is not the correct statement. So option B can be discarded directly. So option A says that on the left side. Yes, partially it is correct. I cannot claim. I need some more facts. Next, option C says that point P lies on the right side of both the spools. Okay. Even this could be also correct, so I'm not discarding it. And option D says that point P lies on the intersection of line joining B and C and GF. BC and GF. This is where I24 is going to lie, at the intersection of these two lines. Alright, so now here this answer, that is option D, is also not logically acceptable. Now let's do the numbering here and try to predict the direction of motion, or the location of I24, I mean. So here if we start with the numbering, so this would be the center of rotation of spool 1, this would be I12, and here between the link 2 and the tape itself, it is going to be a formation of higher pair. So this is I23, and same way between 3 and 4, it's going to be formation of higher pair, that is I34, and this is the center, which is, I mean here, even here also, it is I14. All right. So that's how we are able to mark the eye centers. Next is that I13 has to be collinear with 1, 2 and 2, 3. This is the line joining 1, 2 and 2, 3, and I13 has to be collinear with 14 and 34. So these two lines, I mean the 14 and 34, this is another line, and 12 and 23, this is another line. So where they are intersecting, that is the location of I13. So it's hard to predict that where exactly I13 is going to lie, and that's not the part of our question as well. So we can discard that I13 location. Next is that we are left with I24 marking. So I24 has to be collinear with 12 and 14. 12 and 14. Okay. Same way, I24 has to be collinear with 23 and 34. 23 and 34. So even then, if we try to apply this this condition, we are unable to predict it. Okay. Now here, if you observe the sense of rotation or the velocities of these two bodies, that is velocity of I34, that is velocity of point G, it is causing counterclockwise sense. So this will be upwards. So this would be Vi34, and this is going to be downwards. This is Vi23. So these two velocities has to be maintained the same, so that the belt will remain intact with the pulleys. No slipping or no, the belt will be intact when this winding process or unwinding process is happening. So now if we equate these two velocities, that is velocity of Vi23 is equal to velocity of Vi34, then we can write this as radial distance, that is AB, or radial distance, that is I12, I23, omega 2 is equal to I13, sorry, this is I14, I34, omega 4 it would be. I14, I34, omega 4 it would be. So now here, if you observe 1, 2 and 2, 3, that is the 20r is the radius. This is 20 times of r it is into omega 2. And this is what? This is 10 times of r. This is 10 times of r into omega 2. So we get it as omega 2 by omega 1, omega 4 equal to, that is 1 by 2. Omega 2 by omega 4 is equal to 1 by 2. And if we apply the angular velocity theorem to this side, then it becomes as I14, I14, this has to be I14 in the numerator, I14, I24 by I12, I24 it would be. So here if we try to decode these I centers with the points available over here, then I14 is actually H. I14 is actually H. This is H, and I24 we don't know, and that point has to be P. Okay, that is P, HP, and this is what? AP. A and I24 is that point which needs to be marked. So HP by AP is equal to 1 by 2. We got the condition as HP by AP is equal to 1 by 2, which means AP has to be greater. AP has to be greater than HP. This is AP. Okay, and HP is this portion of the length. So the point P has to lie on the right side. The point P has to lie on the right side, and the hint was given to you indirectly in the question itself. So option C is the answer for this question. Okay, so it will involve a lot of critical thinking, so just be very patient when you find these kind of questions. Dear students, let's see the next question, that is from the GATE 1997. The crosshead velocity in the slider crank mechanism for the given position is shown in figure, where Vc is the linear velocity of the crank pin. So velocity of crosshead has to be expressed in terms of velocity of the crank. Okay, so now if we draw the velocity vectors and the direction of rotation is not indicated, let's assume that crank is rotating in counterclockwise. So as per the direction, this would be the velocity of crank. Let's say this is Vc, and crank is making an angle of alpha with the horizontal. So velocity vector is going to make an angle of 90 minus alpha with the horizontal. So this is the velocity vector which is going to describe the this is going to describe the direction of the velocity of the crank. Okay. Next is velocity of the connecting rod has to be perpendicular to it. Okay. So here PC is representing the connecting rod, and this is the velocity of point P with respect to C. This is going to make an angle of 90 degrees, and the angle here formed within the triangle will be 90 minus of beta it is. Okay. So we have got the two vectors. One is the velocity of the crank VC, other one is the velocity of the connecting rod, and the third vector is as per the direction of rotation of the crank. We can observe that the slider is likely to move towards left side. So this will be velocity of the slider or the crosshead. Okay, it is horizontal. Now using all these vectors, we need to form a closed polygon. Okay, so here velocity VC, let me mark it, and it is making an angle of 90 minus of alpha. Okay, next this is OC, this is OC. So O being the fixed point and C being the moving point. Next I need to place a vector velocity of P with respect to C at the point C itself. Okay, so this is velocity of P with respect to C, and this vector is going to make an angle of 90 minus of beta with the horizontal. Okay, next is velocity of the slider is horizontal. So I need to place this vector, okay, starting from the point O. So starting from the point O, I am placing this vector. So this would be velocity of the slider, that's VP. Now dear students, what we can do is we can apply simply the Lami's theorem, and that is I need to calculate this angle. So the angle would be 180 degrees minus of the remaining angles. So that comes out to be as alpha plus beta. Okay, so 180 minus of 90 minus beta minus of 90 plus alpha. So 180 gets cancelled, we get end result as alpha plus beta. So velocity of piston divided by sine of the angle, that is alpha plus beta, equal to velocity of the crank pin divided by sine of the angle which is opposite to that, it is sine of 90 minus beta. Okay, same way we can also express for connecting rod, velocity of connecting rod, that is divided by sine of the angle which is opposite to that, it is sine of 90 minus alpha. So now here we can write it as velocity of P is equal to velocity of C. This sine of 90 minus alpha can be written as cosine of, sine of alpha plus beta can be written as cosine of 90 minus of alpha plus beta. Next is sine of 90 minus beta can be written as cosine beta, and reciprocal of that is secant of beta. So now we can represent this in another form, that is velocity of crank is equal to cosine of 90 minus of alpha plus beta. So here we can enclose them within a bar itself, and this is sine of secant of beta. So this would be the expression for velocity of crosshead in terms of velocity of the crank pin. Okay, let's check the option. So here based on the option A has got the positive sign, and option B it is VC cos of 90 minus of alpha plus beta into secant beta. This would be the answer. So option B is the answer. Okay, let's see the question. Here consider the triangle formed by a connecting rod and the crank of an IC engine has two sides of the triangle. If the maximum area of this triangle occurs when the crank is 75 degrees with respect to line of stroke, the ratio of connecting rod length to the crank radius is dash. So here do remember that maximum area we will get when the angle between crank and connecting rod, angle between crank and connecting rod is 90 degrees. So when we draw the configuration diagram for that, it would be like this. Okay, this is 90 degrees and this is theta. This is beta, which is angle made by the connecting rod. Okay, so here as per the question it says that theta is equal to 75 degrees. If theta is equal to 75 degrees, this is R, this is L, and the ratio of the connecting rod length to the crank radius. So here we can write it as tan theta is equal to opposite side, that is L, divided by adjacent side, that is R. So tan 75 is equal to L by R. So tan 75 is 3.73. That is option C is the answer. Now let's see the question. In the spur gear having involute teeth, the product of circular pitch, that is PC, which is equal to pi times of pitch circumference divided by number of teeth, that is sometimes we use Z or else, or we also use designate the number of teeth with T as well. And the diametrical pitch, that is PD, is equal to number of teeth per inch of diameter, that is diametrical pitch, that is Z by D it is. Okay, so if we take the product of these two, that is PC into PD, which is equal to pi D by Z into Z by D, this is equal to pi. This is equal to pi. Okay. And same way, if we take the multiplication of module, that is M, with diametrical pitch, module is given by the diameter by number of teeth into and diametrical pitch is number of teeth divided by diameter. So this is equal to 1. So product of module and diametrical pitch and product of circular pitch and diametrical pitch. These are two important results you need to remember. So as per the question, the answer is pi only. Let's see the next question. A 1.5 kilowatt motor is running at a speed of 1440 rpm and it is to be connected to the stirrers, which are running at a speed of 36 revolutions per minute. The gearing arrangement for this application is dash. So here if we compare the ratio, that is ratio of the motor, speed of motor or the driving member or input member, that is n subscript input divided by n subscript output, that is equal to 1440. Let me just correct this. This is 1440 divided by 36. So this is 36 ones and 36 fours, and this 0 will be carried. So reduction ratio is almost 1 by 40 times. So that is only possible, high reduction ratio, and that is only possible when we go with the worm gear. Option D is the answer. So for high reduction ratios, worm gear is being used. So range varies from, if the ratio is from 10:1 to 10 is to 1 to 100:1. So if such is the case, if we are reducing the speed by almost 10 times to 100 times, then the arrangement that is recommended is worm gear only. As per the question, option D is the answer. Next question. Here is the list of gears given to us: worm, crossed helical, bevel, spur gear. So spur gear is used for connecting the parallel shafts. Okay. So as you can see the list here, D is going to match with the 1. Okay. And bevel gears are used when the shaft axes are intersecting, non-parallel and intersecting shaft axis. That is C2 it would be. Same way, crossed helical gears. Crossed helical gears is used when we have got non-parallel and non-intersecting shaft axis. Like this, the shaft axis orientation would be. So if we are saying helical gears, then the application of helical gears is once again for the parallel shafts. Okay. So again, likewise, helical gears, we have the classification under spur gears when the teeth have got some inclination, and this helical gears, even it is used with the combination, or they have a separate group under bevel also. Helical bevel gears are also called as spiral gears. Okay, so that you can see later. So as of now, I mean here, the crossed helical gears, it is used for the non-parallel and non-intersecting shaft axis, that is B3. Same way, the worm gears, it is used for large speed reduction ratios, that is A4 it would be. Okay, so this is the combination, kindly go through it. Next question, an arm OA of an epicyclic gear train shown in the figure revolves counterclockwise about O with an angular velocity of 4 radian per second. So speed of the arm is given as 4 radian per second. Both the gears are of same size. The angular velocity of C if the sun gear B is fixed. So B is fixed. So here when we understand that B and C are the gears, they are in mesh. So let's write it here. Let's write here. Omega C by omega B equal to teeth of B by teeth of C. We can put it this way. And so now here it involves the external gearing. So that's why I need to incorporate a negative sign. And we are not dealing with a simple gear train. We are instead dealing with the epicyclic gear train. So that is why I need to include one more term, that is measuring the velocity of gear C with respect to arm minus measuring the angular velocity of B with respect to arm. That's all. That's all. No need to go for the tabular method. You can write the formula very easily. So now that we know the velocity of which one? The angular velocity, both the gears are of same size, the angular velocity of C when the B is fixed. So this term, that is omega B, has to be 0. If this is 0, then omega C equal to, or omega C minus 4 by 0 minus 4, and both the gears are of same size, so this ratio would be minus 1. So minus 4 into minus 1, that is equal to positive 4. So omega C will be equal to 8 radians per second. Option B is the answer. Okay. Let's see the question, dear students. A flywheel of a moment of inertia 9.8 kg meter square fluctuates by 30 rpm for the fluctuation of energy of 1936 joules. The mean speed of the flywheel is dash. So fluctuation in energy, or delta Ke max, can also be expressed as, that is I into omega max square minus omega minimum square by 2. So this we can later write it as I into omega average into delta omega. Okay, and this is delta Ke max. So here we, instead of delta Ke max, which is 1936 equal to I is 9.8 into omega and delta omega, that is 2 pi n by 60 it becomes. So this is 4 pi square by 3600 into n, it is n average, it is n average, okay, into delta n, it is, next is delta n. So delta n here it is given as 30 rpm, so into 30. So upon solving for n average, we would be getting the answer as 600 rpm, that is option A is the answer. Now let's see the question. A mass of 1 kg is suspended by means of 3 springs as shown in the figure. The spring constants are K1, K2 and K3 respectively. That is 1 kilonewton per meter, 3 kilonewton per meter and 2 kilonewton per meter. The natural frequency of the system is dash. So herein we understood that by seeing the arrangement, K1, K2 are in series combination. So when they are in series combination, the equivalent stiffness is obtained by adding the reciprocals, that is 1 by K equivalent is equal to 1 by K1 plus 1 by K2. Okay, so let me just rewrite this properly. So as it is addition of the reciprocal stiffnesses. So here this comes out to be as K equivalent equal to K1 into K2 divided by K1 plus K2. So here the values of K1 and K2 are given as K1 is 1 and K2 is 3 divided by 1 plus 3. Sorry, here in the numerator we need to have it as multiplication of these stiffnesses. So this is 1 into 3 divided by 3 plus 1. So this is 3 by 4, which is equal to 0.75 kilonewton per meter. So now here the stiffness, the spring K3, if we include both of these two, are going to form a parallel combination. So they are forming a parallel combination. So for parallel combination, directly we need to add the stiffnesses. So equivalent stiffness, that is final one, what we get it as 0.75 plus 2, that is 2.75 kilonewton per meter. So now in the question they have been asked to calculate the natural frequency. So this is natural frequency is given by omega n, which is equal to root over K equivalent divided by m. So equivalent stiffness is 2.75 kilonewtons, which is also approximately 2750. So this is 2750, mass is 1 kg. So 2750 divided by 1 and under root of that. If we try to solve this without a calculator, then 2500, the square root of 2500 is 50. So answer should be somewhere closer to 50. So if you observe, option A is not closer to 50, it's below 50. Option B is 60. The square root of 60 or the square of 60 is 3600. Same way, 52.44 is the more likely answer here. 52.44 radians per second, that is the answer. Okay, so option C is the answer. So the next question, here we find that two identical masses are connected by a single spring, and this is a problem which has got 2 degrees of freedom. It's a 2 DOF kind of a question, and here we see the masses on the either sides, they are same. So let's try to solve the problem by using the mathematical equations or writing the equations of motion. Let's call this as mass as m1, let's call it as m2, although they are equal, and this is x2, the displacement, and let's call this as displacement x1. Okay, so herein, if we try to draw the free body diagram of mass m1, that is, if the displacement x is given, x1 is given to this, the inertia force, that is m1 x1 double dot, is going to resist that. Okay, and now we need to be careful while marking or writing, expressing the spring force. So here the spring force K is interactive between the two displacements, that is x1 and x2. So here with respect to mass 1, the net displacement has to be x1 minus x2. This is the free body diagram for the mass 1. Same way, if I consider it for the mass 2, okay, let me draw that. This is m2 and x2 is being taken towards right side. Even if you take it towards left side, nothing wrong in that, because answer won't be affected here. So here the x2 is towards right side, and the inertia force, that is m2 x2 double dot, is going to offer resistance, and same way even the stiffness will also be interactive between x1 and x2 displacement. So here when we are expressing that displacement for m2 mass, then this term should be taken in the reverse order, that is x2 minus x1, it should be expressed this way. That's how the forces are being, or reactive forces or connecting forces are being transferred from one body to the other body. And this principle we have learned it in the engineering mechanics. Same is being used. It is just that we modify the direction of that reactive force or the connection force that is responsible due to the connection. That is what is here. Here we are reversing the direction of the force when the bodies are getting changed. Okay, so here FBD of 2 it is. So the final equation for this, it becomes as mx1 double dot plus k into x1 minus x2 equal to 0. And next would be m2 x2 double dot plus k x2 minus x1 is equal to 0. Now here, as you go through a spring mass system arrangement, you find that the direction or the displacement x, this is going to be definitely simple harmonic. So here I can express x1 as capital X1 into sine omega t. It's a simple harmonic motion. And X2 will be capital X2 times of sine omega t. All right. Now, if we differentiate this for the first time, it becomes cos omega t into x1 omega. And if we differentiate this further, that is x1 double dot plus, sorry, it's not plus, x1 double dot equal to, this would be derivative of x1 will not be there. Derivative of sine is cos and derivative of cos is minus sine. So x1 omega square into sine omega t it would be, and definitely there has to be a negative sign. There has to be a negative sign. Same way, even for x2 also, it can be expressed as x2 double dot is equal to minus x1, sorry, minus x2, capital X2 into omega square into sine omega t. This is how the displacements would be expressed, and herein we are required to calculate the natural frequency, or how many natural frequency this system is going to have. Okay, so now let's just put these values in the above equations, and we get it as m1 into minus x1 omega square sine omega t plus k into what is small x1. Small x1 is capital X1 sine omega t minus capital X2 sine omega t, and this is equal to 0. So what we get, the final expression, if we observe here, sine omega t, sine omega t, sine omega t will get cancelled, and the coefficients of x1, that is x1, if we take up the coefficient, here we have got k, here we have got k, and on this side we have got minus m1 omega square it would be, plus x2 coefficient, here we have got it as minus k. This is equal to 0. This is equal to 0. So this is the equation of motion, or we have actually converted the equation of motion into an algebraic equation. That's how the mathematics come into existence. So now next, same way we can express even for m2. So for m2 we can write it as m2 into minus capital X2 omega square sine omega t plus k times of x2 minus x1 it is. So capital X2 sine omega t minus capital X1 sine omega t is equal to 0. So once again it gets cancelled, and if we try to write the equation in x1 plus something into x2, what would be the? So here if you observe, the coefficient of x1 is actually minus k plus x2 coefficient is k minus m omega square it would be, sorry, m2 omega square, that's equal to 0. So I need to express this in the lowercase letters. So now here we have arranged these equations in the format of matrix A into X matrix, that is x1, x2 equal to 0. This concept we find it in eigenvalues and eigenvectors. So likewise here it is k minus m1 omega square minus k, and here this is k minus m2 omega square. So for finding the value of omega, this is in the format of a minus lambda I. This is a minus lambda I. So where lambda, or a root of lambda is basically similar to omega square. So root of, or that is under root lambda will give us omega. Okay, so here if we take out the determinant of this, if we take out the determinant, it would be k minus m1 and m2 both are same. So now it becomes k minus m omega square whole square minus k square is equal to 0. So this comes out to be as k square plus m square omega power 4 minus 2 times of k into m into omega square minus k square equal to 0. So k square and k square will get cancelled. And here, once we try to solve for this, or omega square, if it is pulled out, this becomes as m and m square will get cancelled. So this is m into omega square minus 2k is equal to 0. So one of the roots would be omega equal to 0. Another one root would be omega equal to root over 2k by m. That is option A is the answer, guys. Sorry, yeah, option A, that is root over 2k by m. That is the answer. Okay. So next question here, as shown in the figure, the mass of 100 kgs is held between the two springs and the natural frequency of vibration of the spring is dash in the cycles per second. So here you observe that the mass is attached at the interface of two springs. And if the same mass has been attached at the one end of two springs connected like this, then this would have been in series combination. And herein we observe that 20 kilonewton spring on the top is going to experience the extension, and 20 kilonewton spring at the bottom is going to experience compression. So tension of the top equal to compression of the bottom, and that's when these springs will form a parallel combination. Understand that this is a series combination and this is straight away parallel combination. Don't get confused, because you will be finding a similar kind of analogy even in other parts, in the other subjects as well. Okay, so here the directly stiffness will be equal to, that is K equivalent will be summation of these two stiffnesses, that is 40 kilonewton per meter, and mass is equal to 100 kgs. So omega n, that is natural frequency, would be equal to root over equivalent stiffness by m, and that is equal to 40 into 10 power 3 divided by 100, and that's equal to 40, that is 40,000. 40,000 by 100 will be 400. 400 under root of that is 20 radians per second it would be. And here the frequency has to be expressed in hertz or cycles per second as well. So Fn is equal to 1 by 2 pi times of omega n, which is equal to 1 by 2 pi into 10, that is, it is 20. So which is equal to 10 by pi cycles per second. So cycles per second or hertz, both are the same. Okay, so option C is the answer, guys.